Hello, we're the Dreamer Duo, and today we're going over Module 3, Chapter 4 and 5, Number 3, and Integers.
I'm Masheka.
And I'm Annabeth Hrdlicka.
Okay, let's
start with question
1. There you go.
Okay, so question 1. Use the divisibility test to decide which of the numbers 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11 is a divisor of the numbers in the left column of the following table. The number 684 is done for you. Demonstrate a neat chart and explain divisibility for numbers 2, 4, 5, and 6. And then 10, show your work to apply the divisibility rules for 3, 7, 9, and 11. Write yes or first for each number, then explain with an explanation. So you write yes or no if it's divisible or not. So to solve this problem, you have to know the divisibility rule for each. Oh, sorry. So this is the chart. So I have a question for you on this one.
Yeah.
Okay, so we usually count in tens when we the tens place in math. That's the basic, and our base is usually 10. So for the divisivity test rules, what is the rule for number 11?
For number 11? Number 11 is a little tricky. For number 11, you have to actually add the odd numbers and then add the even numbers. And when you add them, then you subtract them. If the number is equal to 0 or 11 or divisible by 11, that whole number is divisible by 11.
Okay, thank you. That is different. That makes a lot more sense.
2 and 3 is actually simple to solve. 2, you just have to see if the last digit is even or odd. For 3, you have to add all the digits and see if that whole number that number is divisible by 3.
Okay, so
I do have a question for you for number 6. 4, you have to be divisible by you have to do the last two numbers. 5 have to be a 0 or 5 as the last digit. I do have a question for you for 6. 6 says you have to be divisible by 2 and 3. Why do you have to be divisible by 2 and 3 to be divisible by 6?
Okay, so it is one of the divisibility tests. Yeah, that's a answer. So it's one of the rules. So it makes sense because 2 times 3 equals 6, and also 2 and 3 can both fit into 6. So that's why.
That's awesome. I didn't even know that.
6 is one of the simple ones compared to 11.
Yeah, it sounds simpler than 11. But yeah, it just seems that we just use the divisible rules to solve these numbers, I think. So let's move to question 2.
Yes, ma'am. So question 2.
I don't know where to move this.
You have to demonstrate the processes of nines to check each of the following answers. So to solve these A through D, you have to add each digit in each set, then you will add each digit in the given answer. When you add those digits, both the problems and the solutions, you will compare the added digits and numbers. If the numbers match you, that means that the answer is correct. But if the answers are different, that means that it's incorrect. So if it's incorrect, you have to solve it and get the correct answer, but it's correct, you don't have to do that. But you always have to, the whole thing, you have to exclude number 9 to make it work. So,
yes.
I have a question for you on this one.
Go ahead.
So, we see all this, and my question is, could a student use the processes of 9 to check their work?
You actually can. When you use the process of nines, you can see if it all equals up to each other. If it does, um, if it does equal up, it means that it's right. But if it do not equal to the process of nine, then it is incorrect. So you can use the process of nine to see if it equals out to the original or to the sum it's supposed to be.
Okay, thank you. That's a good way to check.
It is. I do have a question. Like these, you see, our first few examples are addition, but when we get to our third and fourth problem, we see that the signs change. Like instead of addition, we see subtraction. So would it matter what sign you use to solve this problem?
Well, for this one, for adding and subtracting, it does not matter. The only thing that matters is if either you're adding to the problem or taking away from it. So for this one, you don't have to look into PIMDIS yet because it doesn't get that complicated. It's just adding and subtracting. So the only thing that matters is if you're adding or subtracting. So nothing else changes. You don't have to worry about anything else.
Good. So for the whole problem, I don't have to worry about it until the answers incorrect are correct. Got it. Thank you. That saves a lot of time.
Of course.
Uh, the third one, we on the third question. The third question is we have to find what rod can go into the number of rods they give us. The first rod they want us to solve for is 9. And I do have a question for you on this one. And that is why would it be easier to know the multiples to solve this question?
Well, since we're looking for a 9 rod, that's like the whole point. It makes it a lot easier because, well, that is literally what we're searching for is a 9. So that's probably one of the simplest ones to do. So since it fits what we're looking for, if you look at 9, you see that the equal is 1 times 9, 9 times 1, or 3 times 3. And those are really simple multiples, and it fits perfectly already. So simple either way. So it is just a more simple one.
It is simpler. Got it.
Yes, of course. So for this one, you'd say the same thing. Like 6 would probably be the most simple because it's what you're looking for originally.
So we just have to know the multiples, and knowing the multiples will make it easier. Thank you. You answered that wonderfully.
Of course. Of course. I have a question for you on.
Yes.
So you see the common divisors, the greatest ones. So my question is, will there ever be a least common multiple, like divisor, that doesn't include 1? Or will it always have 1 for the least common?
Usually it is usually 1 for the least common divisor because it is a prime number. But if we're talking about non-prime numbers, like if we have a fraction, then sometimes the fraction would be the least common divisor. But usually without fractions, most of our problems are not fractions and we use prime numbers. So with that, 1 will usually be the common divisor, the least common divisor. But if we're not talking about prime numbers, then sometimes it will be a decimal or a fraction.
Okay, thank you. I didn't even think about a fraction, but that makes a lot of sense.
Let's go to the next question. This is question 4.
Okay, so question 4, you have to demonstrate the use of this method to find the least common number form in parts A through C in prime power form. So you have to find like the least common, the lowest number, but it's like the most common one for this one. So they have to have it in common. So to solve this problem, you first need to know what your prime numbers are. For each number, you will factor out the prime numbers, When you have all the numbers and their prime multiples, you will compare the numbers. If a number repeats in that same row, you will only use the number once.
So I do have a question for you, Annabeth. I see that there's only a few prime numbers. My question for you is there why the other numbers will not be considered prime?
Well, for a prime number to be considered prime, it only has to have two factors. So they are not prime numbers because they can be multiplied by more than just one in their original number. So you see 2, for example, you can only multiply it by 1 times 2 for it to work. Same with 3. But for 6, it can be 3 times 2 or, 1 times 6. And then for some, it keeps going like more. They're going to be 3 multiples, 4, 5, 100, just the bigger numbers.
Oh, that's a smart way to think about it.
Thank you. Of course. I have a question for you as well.
Yes.
So what would a non-prime number be called?
That would be actually called so the the name for a non-prime number would be a coefficient number.
Thank you. That's a good vocab word to know for sure.
Sorry.
It's okay.
Okay. Let's go ahead and go to the next question. But to solve this question, we'll have to know the prime numbers and then keep dividing the least prime number. And when we keep dividing the least prime number, then we'll divide it for all the other numbers, and then we see what they all have in common. And then finally, we'll raise that to the power, but we will only use it once or twice during a row. In case.
Okay, that's cool.
Okay. We have question 5 here. So question 5, they want us to know they have each circle has a number of teeth. We have 48 teeth, and then we have an 84th teeth wheel. So what we have to do is we have to see how many times it will have to turn to get to the same exact spot that they're both in. And then we have to see how many times a wheel will have to turn more than the other. It will do the subtracting. So we'll first, to solve this problem, we'll have to do the multiples of each number. So 48 and 84, these are the multiples. And then we see that they both have 336 in common. And I have a question for you. What would 336 be considered a least common multiple or a greatest common multiple?
For this one, it says that it would be a least common multiple because it is the one number they have in common. And that's what it says. It's the one they have in common will be their least common multiple. So that is why it's the answer, because that's what it shows us. And you can see it down here when you actually solve it that there is only one, so it adds up. And I have a question for you as well on this one.
Go ahead.
So does this problem have both a greatest common multiple and a least common multiple, or just one of those?
Well, if we keep continue the numbers, it will have another common multiple, but it will be so far into the problem, you'll have to keep adding, and then because it will keep continuing to get in the same place, so it will have a greatest and a least common multiple, but it will take a while for it to reach the greatest common multiple again.
Okay, but just for this one right here, so far no, but in the future, yes.
In the future it does, but just for the numbers right here, it does not have a greatest common multiple for the one.
Thank you.
Right here. Okay, let's go to the last question. Okay. So for this one, they want us to make a magic square. And by using these numbers right here that they give us. I do have a question for you on this problem.
Yes.
The question is, will we be able to use a number more than one time?
So to use a magic square, the rule is you are not able to use the same number twice. So it is a good idea, as you've done up there, to cross them out after usage. So if you do use it more than once, it'll mess up the whole square and it can't work. So good job crossing it out to avoid any confusion.
Okay.
And I have a question for you on this one as well. So how do you find the magic number for this table?
To find the magic number for this table, each table have a different magic number, but to solve this one, you'll have to multiply how many rows it is by how many columns it is. So as we see, we have 3 rows and 3 columns, so 3 times 3 is 9. So our magic number is 9, or in this case, it is -9, but it's still the magic number is 9.
Thank you. That's awesome. That's a great way to explain it and easy to catch on to as well.
Yeah, you explain things very well.
Thank you. So do you. That's why we're the Dreamer Duo.
Well, that's it for this presentation.
Yes, thank you everyone for watching. I hope you guys understood everything well and enjoyed.
I really do. Sorry if I complicated things a little bit.
No, nothing was complicated. I know how to do some math after this lesson.
I do too.